Hello, everyone. This is our presentation for our final project. In this final project, we use open flight data set with over 10,000 airports, 5,888 airlines, and more than 67,000 routes between 3,000 airports and more than 500 airlines spreading all around the world. With that, we found all possible destinations from an airport and mapped all of them on a world map and sorted based on between a centrality. The visualization is based on the idea of a heat map. A higher centrality is mapped on the output PNG with a larger circle and a brighter color. And a higher centrality basically means an airport is more connected and more important in a sense. First, I'm going to talk about our testing strategy. We divided our testing into three subcategories. Test initialization, and between a centrality and initialization, we test whether we read the database correctly, and we test whether we set our adjacency matrix correctly, and then we test centrality using two very basic graph. After that, we test our centrality using our real database. Then we test coordinate conversion, which converts a latitude and longitude onto an XY pair into our PNG. And the last part of our test is test whether we draw the graph correctly. So I'm gonna run the test now.
So the first algorithm we use is the betweenness centrality algorithm, which calculates the shortest path between every pair of nodes in a connected graph using BFS. Each node receives a score based on the number of these shortest paths that pass through these nodes. Nodes that most frequently lie in this shortest path will have a higher betweenness centrality score. The first step of this algorithm is to find the shortest path between every pair of nodes and record their dependencies. Let me use this simple graph as an example. First, add node 0 to queue and take every node from the queue to stack and record the distance of every child, and namely its neighbors. So first take 0 from the queue, add to the stack, and add 1 and 2 to the queue, and update corresponding distance sigma, which records the number of shortest path from the source and updates predecessor list. Then perform the same calculation to node 2, node 1, node 4, node 3, and the remaining node 5 and 6. Now we have all the shortest path calculated and their predecessors recorded. The second step is to perform the centrality accumulation. To do so, we take every node from the stack and visit its predecessors and calculate delta, which is array record dependency from the source, and calculate the corresponding centrality score. So first calculate the centrality of node 6, then node 5, node 3, node 4, node 1, node 2, and finally back to the source, node 0. So by now, we have successfully calculated all the dependencies starting from the source, which is node 0, and get corresponding centrality score. To do so, to get the final result, we have to visit every node and treat it as the source. So after that, we have to visit node 1, node 2, and all the way to node 6. And we got the centrality score of this undirected connected graph. However, in our project, airports and airlines are not strictly undirected, which means there could be a flight from airport A to B, but then not necessarily from B back to A. So we have to divide all the centrality by 2 to get two-way centrality score, which is this graph as the final result. And by using this algorithm, we have successfully calculated the centrality of all airports and draw them onto the PNG.
The second part is to present centrality onto world map as heat map. This can be done in 2 steps. First, we project the position of each airport onto the map based on the data we retrieve from dataset by converting the longitude and latitude of each airport into X and Y coordinates. The following equations place the x-axis of the projection on the equator and the y-axis at longitude. Then we project the position of each airport by using the BFS to change the target pixel hue. We will get the base hue according to the centrality we computed. Then we push the pixel into the queue. The upper, down, left, and right pixel will also be pushed into the queue. The hue of these pixels will be calculated based on the distance between current pixel and base pixel. The further the distance, then the number of hue will be closer to 270. When the number of hue is larger than 270, we will stop changing the hue of the pixel. After traversing the whole map, we will be able to change all the target pixels' hue based on the centrality. To visualize the output, we include animation class to create animated images from a sequence of PNG objects as frames of animation. It shows the process of how to project onto the map. Individually, I really like the way of visualization because it is straightforward to show the goal of the project. Based on the output heat map, we can find out which several airports have the most important effect on the transportation easily.